Hello and welcome to this video. Today we are going to explore an interesting topic in the field of operations research and optimization, and it is job shop scheduling. In this video, we'll be working through an example of how to solve a scheduling problem using the programming language Julia and the optimization package Jump. And we will also be using a powerful solver called Simplex to find the optimal solution to our problem. So, what is job shop scheduling? Simply put, it is about the best order in which the task should be performed to be optimize some measures of efficiency. And let's say a manufacturing setting where you have different jobs and each job is made up multiple tasks. These tasks need to be completed in a certain sequence on different machines. The goal is to schedule these tasks across all jobs in a way that minimizes the overall time to complete all jobs, which is called the makespan. And job scheduling is a classic optimization problem, and it is commonly found in manufacturing, production planning, and various logistics applications. It is considered a combinatorial optimization problem, and that meaning uh, as the number of tasks and machines increase, the number of possible solutions grow rapidly. Therefore, finding the optimal schedule becomes computationally intensive. And in this video, we will talk through the code to set up and solve this problem using Julia. And specifically, we will define the problem data, which includes the tasks and machines involved, and formulate this scheduling problem as a mathematical optimization model using JUMP, and it is packaged in Julia, and set constraints and variables to represent the scheduling requirements, such as ensuring tasks within a job follow the correct order and no two tasks on the same machine overlap, and optimize the schedule using the Simplex solver to find the minimum makespan, which is the shortest time to complete all tasks. And the purpose of using an optimization algorithm like this to automate complex scheduling decisions that would otherwise be very difficult to handle manually. And by the end of this video, you will learn how to code a solution in Julia and gain an understanding of how mathematical optimization helps in solving real-world scheduling problems efficiently. So let's start by walking through the initial part of the code. And the first thing you will notice is that we import two Julia packages, jump and simplex. First, jump. It is a modeling language for optimization problems. It makes it easy to define decision variables, constraints, and objectives in a way that's very readable. And simplex here. Simplex is the solver we will use, and it is an optimization engine capable of solving large-scale problems, including linear programming, mixed integer programming, and others. And by importing Simplex, we tell Jump to use this solver to find the optimal solution to our scheduling problem. Next, we define our problem data. We use a constant called jobs, here you can see, to represent the task involved in the scheduling problem. Jobs is an array where each element corresponds to a different job, and each job is represented by a list of tasks, and each task is defined as a tuple with two elements. First, the first element of the tuple is the machine on which the task is performed, and the second element is the duration of that tasks. And for example, job 1 has three tasks. The first task is performed on machine 1 and takes 3 units of time. The second task is performed on machine 2 for 2 units of time, and the third task is on machine 3 lasting 2 units. And Job 2 and job 3 are represented similarly, each with their own sequence of tasks and durations. And after defining the jobs, we introduce two more constants. First, num underscore jobs. Here, it is the number of jobs, which is simply the length of the jobs array, and this will help us iterate through each job later. And num underscore machines is the number of machines available. In this case, we have three machines as represented in the task of the jobs. And I hope this part is okay. And let's switch and let's look at the create part at variables and constraints. By the way, like that. Okay, let's move on. And here, creating model, these parts. We start by creating an optimization model, and here we use model simplex.optimizer to initialize a new model that will use the simplex solver to find the optimal solution. And in the optimization problems, we need decision variables. These are the values we want to determine, and they must satisfy certain constraints. And let's look at this part, what's happening. At first, these lines, 17 line, here you can see, this variable represents the start time of each task for each job, and it is a two-dimensional array indexed by the job number and machine number. And here you will see what is this? It is a constraint indicates that the start times cannot be negative, which makes sense because tasks must start at some point in non-negative time. And here second line variables 18. So what is it? And what is makespan? Makespan is the variable we want to minimize, and it represents the total time taken to complete all jobs. By minimizing makespan, we are effectively trying to find the schedule that completes all tasks as quickly as possible. And here 19 bin variable, you can see what happens here. It is a three-dimensional binary variable array, and each entry in bin is either 0 or 1, and it is used to enforce ordering constraints for tasks on the same machine. It indicates whether one job's task comes before another on a specific machine. We will see how this is used in the constraints later on. And we will look at constraints, and here you can see it's starting with 21 and ending in 26 line. So constraints are the rules that our variables need to follow, and here we add the first set of constraints which ensure that tasks within the same job are performed in sequence, and we iterate over all jobs using for job in one num jobs. And here you can see, so for each job we iterate over its tasks. Since tasks are performed sequentially within a job, the start time of each subsequent task must be greater than or equal to the start time of the previous task plus its duration, and this is what the constraints enforces. And specifically here you can see in the 24th line, here you can see, and here start job tasks plus 1. Here it is the start time of the next task, and start job tasks, here you can see, sorry, okay, now this is, and these two is the end of time of the current tasks. By enforcing that the next task starts only after the current task finishes, we maintain a sequential order of tasks within each job. So let's look at this loop. We have a loop here, and here what we can say, what happens here. In this part of the code, we add constraints to ensure that tasks sharing the same machine do not overlap. And let's go through the logic step by step. What happens here? For each machine, we iterate over all the machines using for machine in one and none machines. And this loop will handle constraints for tasks that need to be scheduled on the same time machine. Same machine. And for each pair of jobs, we loop overall pairs of jobs and job 1 and job 2. You can see job 1 and job 2 here. And the key here is that job 1 should not be equal to job 2 because we only want to add constraints between different jobs. And the inner if condition checks, you can see it checks whether both task 1 and task 2 are performed on the same machine. Specifically, here, jobs and jobs 1 and tasks here you can see, here uh, specifically you can see here. And what is it? This ensures that we only consider tasks that need to be scheduled on the current machine. And you will see constraints at one and second. And what happens here? Let me select like that. It's better. Okay. If two tasks share the same machine, they must not overlap in time. To enforce this, we introduce two constraints using binary variables, and first in the 33 and second 34 line. First, here, this constraint ensures that if job 1's task come before job 2's tasks on the same machine, then job 1's task must finish before job 2's task starts. And the binary variable, and it is bin and job 1, job 2 machine controls this ordering. If bin job 1, job 2 machine is 0, the constraints forces job 1's task to finish before job 2's task begins. And the large constant 1000 is used as a big M value, effectively allowing the constraint to be inactive when bin job 1 job 2 machine is 1. And second constraints, let's look at this line. So this constraint works similarly but in the opposite direction. It ensures that if job 2 task comes before job 1's task on the same machine, then job 2's task must finish before job 1's task start. And if being a job 1 job 2 machine is 1, this constraint becomes active and it enforces the required ordering. So together, these two constraints ensure that tasks sharing the same machine are properly ordered so they don't overlap. And the binary variable being job 1, job 2 machine, you can see, for example, it essentially determines the order of tasks on the machine. Either job 1's task comes before job 2's or vice versa. And by iterating overall pairs of jobs and tasks on each machine, we ensure that no machine is ever double booked. This is important for finding a valid schedule that respects machine availability and job sequencing. And We have another loop, for loop here. Uh, it's starting with 41, and what happens here? Let's talk. Here we enforce the makespan constraints and iterating over jobs and tasks. Here we loop our each job using for job in one num underscore jobs, and for each job we loop over all its tasks using for task in one length jobs job here. And again constraint, and what happens here? These constraints ensures that the completion time of every task in every job is within the makespan. And here start, you can see, for example, job task is the start time of the task, and job task 2, and here here it is its duration. The sum of these two values represents the time when the task finishes, and by requiring this sum to be less than or equal to makespan, we ensure that all tasks finish no later than the overall makespan of the schedule. And what is the purpose of the constraint here? The makespan variable is the value we are trying to minimize in our optimization, and it represents the total time required to complete all jobs. This constraint ties the makespan to the finish times of all tasks, making sure that is at least as large as the time required to finish the longest running task across all jobs. In simple terms, this constraint is saying the schedule should be short enough to fit within the makespan, but the makespan must also be large enough to accommodate the completion of every single task. And I hope this loop is okay and you understood this. And let's look at the our objective and this part here and here. What happens here? And objective function, setting the objective part and objective model min makespan 48. This line tells the model what we want to achieve, and in our case we aim to minimize the makespan. And the keyword min, you can see second parameter, it specifies that this is a minimization problem and makespan is the variable we are trying to minimize. Essentially, the solver will find a schedule that completes all the tasks in the shortest possible time. And what is this? Optimize and model. What happens here? This function call triggers the optimization process, and the solver will use the defined objective and constraints to search for the best possible solution. It will calculate the optimal start times for all tasks in all jobs that minimize the makespan. And print solution part, what happens here? Print ln and objective value model. After the optimization is complete, we print the value of the makespan, and this tells us the optimal total time required to complete all jobs. And again, we have a loop, for loop, and what is this? We loop over each job and task again, just like we did when setting up the constraints. And for job in one nubs and for task in one length, sorry, here you can see what happens here. It iterates, these two lines iterate our jobs and their respective tasks. And again, print part, what is this? For each task we print its start time, which has been calculated by the optimizer, and value start by test start job task. Okay, it extracts the optimized start time for that particular tasks. And if you are ready, let's look at our output. Let me Okay, we will run. I think it's running now. By the way, let's do that, and we will see. Okay, working. Okay, now what happened? We will look at these parts and we will talk. First, uh, try aggregator one time. What is it? This means that Simplex has applied an aggregator step to simplify the model, and this process combines or removes constraints and variables that are redundant or unnecessary, making the model smaller and easier to solve. And MIP resolve eliminated 0 rows and 14 columns. What is this? The resolve step was able to simplify the model by removing 14 columns, which corresponds to variables in the problem. However, no constraints were eliminated, I mean 0 rows. And let's look at this line. Reduce MIP has 41 rows, 33 columns, and 110 non-zeros. What is this? After the pre-solve step, the model has 41 constraints, 33 variables, and 110 non-zero elements in the constraints matrix, and the non-zeros here give a sense of how dense the problem is. And this line reduce MIP has 14 binaries, 0 generals, and 0 source, and 0 indicators. The model includes 14 binary variables, and there are no general integer variables and spatial ordered states here, spatial ordered sets or indicator constraints. And here resolve times, you can see the resolve step was very fast, taking essentially no time. And here probing time. Probing is a process used to analyze the binary variables in the model, and it also took no significant time. And what we can say here, again, same things. What we can say, for example, click table members. What is it? A click table is used to handle binary variables that are mutually exclusive, and here 14 members are part of this table, which helps Simplex efficiently manage the binary. And what we can say, MIP emphasis, balance, optimality, and feasibility. What is this? The solver has been set to balance finding a feasible solution quickly and improving the solution quality over time. And dynamic search. What is it? MIP search method. Simplex uses dynamic search strategy, which is more adaptive compared to traditional branch and bound approaches. And parallel processing, I mean parallel mode deterministic, using up to 4 threads. What is this? This all runs in parallel mode using up to 4 CPU threads to improve performance while ensuring results remain consistent across runs. And root relaxation solution time. Here you can see what is this. Root relaxation is a version of the problem where the integer constraints are relaxed to allow continuous values, and solving this relaxed problem helps a guide to search for the optimal solution. And this setup was also very quick, taking 0.02 seconds. And we have a table here. It starts with notes at elapsed time. What are they? Here, this part of the output is a progress table from Simplex, which gives details on how the solver is navigating through the optimization process. And each row shows a different stage in the search for the optimal solution, and the columns provide important information about the solver's progress. And let's break down the key columns. First, notes. This column indicates the node of the branch and bound search tree that Simplex is processing, and the number of nodes reflects how deep or how extensive the search process is. At 0 and 0 plus, the solver starts from the root node and it is 0 and explores possible solutions as it branches out. And here you can see start symbol. It indicates a solution that is feasible or potentially optimal. And objective here, this shows the value of the current solution at each node, and it is the objective function's value that is being optimized at that particular node. And best integer, what is this? This is the best feasible solution found so far by the solver. Initially 12.000, which represents the highest makespan the solver is considering. Over time, this value gets updated as better solutions are found. And base found and gap, what are they? Base found, this is the base bound on the optimal solution now so far, and in mixed integer programming, the solver maintains an upper and lower bound on the optimal value, and as the search progresses, these bounds get tighter. And cap, this is a percentage gap between the best integer and best found. It indicates how close the current solution is going to being optimal. For example, the gap is 67%, showing that the best feasible solution and the best bound are quite far apart. And as the solver progresses, the gap reduces to 0, indicating that the optimal solution has been found. And let's look. Cuts, for example, Simplex applies various types of cuts to reduce the solution space and improve solver efficiency, and each row in the table mentions how many cuts were applied up to that point. And for example, cuts 12 means that 12 cuts have been applied to tighten the model. And what is it? It, C, and T. I mean iteration count. That's iteration count. This is the number of iterations the solver has gone through, and it's a measure of how much work has been done by the solver to reach the current point. And for instance, the iteration count is 44, indicating 44 iterations have been performed. And what we can say, I think it's okay. And let's look at the most important part. Here, objective value makespan 10. The makespan is the total time taken to complete all jobs, and in this case the optimal makespan is 10.0 units of time. This value is what we aim to minimize in our optimization model, and it represents the shortest possible schedule that completes all tasks across all jobs. And next, we have the start times for each task within each job, and let's go through them job by job. And job 1, task 1 starts at 3, and the first task of job 1 is scheduled to begin at time 3.0, and task 2 starts at 6.0, and the second task of job 1 begins at time 6, which represents the duration of task 1, and task 3 starts at 8, and the third task of job 1 begins at time 8, right after the completion of task 2, and job 2, let me select here, task 1 starts at time 0. The first task of job 2 starts at time 0, which means it is one of the earliest tasks to begin, and task 2, the second task of job 2 starts at time 2 immediately after task 1, which has a duration of 2 units of time, and task 3 at 3, the third task begins at time 3.0, continuing right after the second task finishes, and job 3 and task 1. The first task of job 3 also starts at time 0, indicating that it runs concurrently with task 1 of job 2, and the second task of job 3 begins at time 2, just after the first task finishes. So this schedule effectively utilizes parallelism, where multiple tasks from different jobs are run on different machines simultaneously. For example, job 2 and job 3 start at 0, making full use of the available machines, and the order of tasks within each job is respected, and no two tasks on the same machine overlap, as enforced by our constraints. And the max span of 10 is the shortest time within which all tasks from all jobs can be completed given the constraints. And this part, what happens here? Click cuts applied to click cuts are applied to improve the efficiency of solving the binary variables in the problem, and a click is a set of binary variables that are mutually exclusive, meaning that only one variable in the set can be one. And by adding these cuts, the solver can better understand the relationship between variables and more quickly eliminate infeasible solutions. And in this case, two click cuts were applied, and implied bound cuts applied 7. Implied bound cuts are used when the solver detects that certain variables are forced to take certain values based on other constraints. Essentially, these cuts impose tighter bounds on variables based on the logical implications of the problem's structure. And by tightening these bounds, the solver reduces the number of possibilities it needs to explore, leading to a faster solution. A total of 7 implied bound cuts were applied, and mixed integer rounding cuts applied. What is this? Mixed integer rounding cuts are derived from the linear relaxation of mixed integer programming problems. They help to round off fractional solutions to the nearest valid integer solution. And this helps the solver find feasible integer solutions more effectively by ensuring that the problem's relaxation doesn't include infeasible solutions. And 3 MIR cuts were applied in this case. And Gomori fractional cuts applied too. What is it? Gomori fractional cuts are among the most commonly used cuts in the integer programming, and they are based on the fractional part of the solution to the linear relaxation and are used to cut off infeasible fractional solutions, thus tightening the feasible region. And Applying these cuts can significantly enhance the solver's ability to converge the optimal integer solution, and here two Gomor fractional cuts were applied. And that's all for our video. Mm, we learned Splex jump and job shop scheduling, and we have machines and tasks, and we code it in Julia, and we have learned how we can interpret the outputs and tables. Here we have two tables and some output reports. And thank you for your listening and attention. See you in the next video.